Take a deep, slow breath in, and as you release it, let the weight of your body settle completely into the mattress. Close your eyes and let go of the day, allowing the quiet, dark space behind your eyelids to become a launch pad into the vast and comforting cosmos. We begin our journey on a very specific day in human history, February 14th, 1990. On this day, a robotic ambassador from our world, the Voyager 1 space probe, was instructed to do something it had never done before. By this point in its grand voyage, Voyager 1 was exactly 3.7 billion miles away from Earth. To put that magnificent distance into perspective, it was 6 billion kilometers out in the freezing dark, or 40.5 astronomical units away from the warmth of our sun. At that immense range, the frantic noise of our world is reduced to absolute perfect silence. Imagine floating seamlessly beside this marvel of human engineering. The Voyager 1 spacecraft weighs a modest 1,592 pounds, about 722 kilograms, roughly the mass of a small automobile. Yet, it is gliding through the frictionless vacuum of deep space. It is traveling at a staggering speed of roughly 38,000 miles per hour, which is about 17 kilometers every single second. Yet, out here in the void, where there are no landmarks to rush past, this incredible velocity feels like complete and utter stillness. You feel no wind. You hear no engines. There is only the slow, quiet drift through the endless ocean of space. Bolted to the side of this silent traveler is the golden record, a 12-inch gold-plated copper disc. In your mind, you can almost reach out and trace the cool, textured grooves of its metallic surface, holding the encoded sounds of rustling leaves, heartbeats, and gentle greetings from a distant home. Here is something remarkable to consider as you rest. It was astronomer Carl Sagan, a member of the Voyager imaging team, who campaigned for nearly a decade to make this moment happen. The probe's primary mission to photograph Jupiter and Saturn had long been completed. It was heading outward, preparing to leave the solar system entirely. Sagan asked that before the spacecraft plunged forever into the interstellar dark, it be commanded to turn its cameras backward, to look over its metallic shoulder one last time, and take a family portrait of the solar system. The maneuver itself was a slow, deliberate ballet. To find the Earth, Voyager had to angle itself precisely 32 degrees above the ecliptic plane, the invisible, flat disk where the planets orbit our sun. Picture the spacecraft slowly pivoting in the dark. There is no sound of whirring motors, only the quiet transfer of electrical commands inside its pristine, insulated heart. Out here, the environment is intensely, beautifully cold. The ambient temperature surrounding the spacecraft is roughly minus 355 degrees Fahrenheit, which is a mere 58 Kelvin. It is a deep, preserving chill, a clean and absolute cold that wraps around the probe like a heavy velvet blanket. But within this freezing silence, Voyager is awake, its instruments humming with the faintest internal warmth. Voyager opens the shutter of its narrow-angle camera, an instrument equipped with a 1,500-millimeter focal-length lens. This lens is designed to peer across billions of miles of empty space, and what it captures is almost impossibly fragile. In the photograph that would become known to the world as the pale blue dot, Earth is captured as a microscopic speck. You might wonder just how small our entire world looks from 3.7 billion miles away. In the raw data returned by the camera, the Earth takes up just 0.12 pixels. It is less than a single pixel in size, a fraction of a dot. Every mountain, every ocean, every continent, and every memory ever made on our planet is compressed into a pinpoint of light so small that it is barely distinguishable from the quiet static of the background cosmos. The color of this tiny speck is deeply soothing, a pale, gentle blue. This color is not just the reflection of our vast rolling oceans, as one might assume. The blue hue is primarily the result of Rayleigh scattering. This is the very same physical phenomenon that makes our daytime sky blue. The short wavelengths of the sun's light are caught and scattered by the nitrogen and oxygen molecules in our thin, delicate atmosphere. Even from the edge of the solar system, the invisible blanket of air that gives us breath is broadcasting a soft, sapphire light into the dark. And Earth only appears at all because of a measurement known as its albedo. Our planet reflects approximately 30% of the sunlight that strikes it. This scattered light, bouncing off clouds and ice caps, travels across the vastness of the void, shining just enough to be caught by Voyager's waiting lens. In the final famous image, you can see Earth seemingly suspended in a hazy golden sunbeam. But the truth behind this beam is a beautiful accident of physics. While that streak of light is not a physical ray of sun piercing the dark of space. Rather, it is scattered light, a reflection bouncing off the inner workings and sunshade of Voyager's own camera optics. Earth just happened to be caught directly in the center of one of these scattered rays, cradled gently in a band of optical geometry. Think for a moment about the journey of that light. The sunlight that warmed the Earth on that February day took about 8 minutes to travel from the sun to our planet. After reflecting off the atmosphere, those tiny photons of light had to travel outward, plunging through the cold expanse of the solar system for 5 hours and 36 minutes just to reach Voyager's camera lens. And then, the data had to make the long journey back home. Voyager transmitted this magnificent image using a radio transmitter that operates on just 20 watts of power. That is less power than the small, dim light bulb sitting on your bedside table. These faint radio waves spilled out into the void, traveling at the speed of light, journeying another 5 hours and 36 minutes back to Earth. By the time this signal washed over our planet, the energy of those radio waves was incredibly, almost incomprehensibly faint. The signal arrived on Earth at a strength of less than a billionth of a watt. It was a whisper in the cosmos, a digital sigh drifting down through our atmosphere. To catch this delicate whisper, humanity relied on the Deep Space Network, giant 70-meter-wide parabolic antenna dishes, massive metal bowls located in Goldstone, California, Madrid, Spain, and Canberra, Australia, slowly turned their faces toward the sky. They listened closely, patiently catching the fragmented data as it dripped back to Earth at an incredibly slow rate. It took months to fully download and process the data, assembling the image line by line, pixel by fraction of a pixel. The pale blue dot was actually not a solitary photograph, but part of a much larger mosaic. It was just one of 60 individual frames that made up the first and only family portrait of our solar system. Voyager managed to capture 6 of the planets in this sweeping view, but space is vast and the planets are small. Mercury was entirely lost in the brilliant, blinding glare of the sun. Mars, our red neighbor, was too thin a crescent to be resolved by the camera at that angle. And Pluto, resting in the frozen outer reaches, was simply too small and too dark to be seen. To capture the color of our world, Voyager's camera did not take one simple color snapshot. The final image of the pale blue dot was carefully synthesized from 3 separate images. Voyager snapped the shutter 3 times, passing the light through three distinct filters: a green filter, a blue filter, and a violet filter. When these three layers of light were sent back to Earth and gently laid over one another, they revealed the true, delicate hue of our home. Shortly after this historic sequence of 60 images was taken, a command was sent from Earth to Voyager 1. The engineers instructed the spacecraft to turn its cameras off and to leave them off permanently. Operating the cameras required internal heating, and the spacecraft needed to conserve every precious drop of its nuclear power for the long, blind journey into interstellar space. The pale blue dot was the very last thing Voyager 1 ever saw. It closed its eyes, wrapped itself in the dark, and continued its silent glide outward toward the spaces between the stars. As you lie here, safe and warm, let your mind drift with the probe. Imagine the deep comfort of that immense distance. Out there, surrounded by the velvet blackness, the Earth is nothing more than a dust mote suspended in a sunbeam. All the urgencies of the day, all the heavy thoughts and complex worries are reduced to a single microscopic point of light, billions of miles away. You are untethered from the gravity of your daily life, drifting in a vast, peaceful ocean of space where time slows down, and everything is perfectly, beautifully quiet. The chill of the void does not touch you. Instead, it is a barrier, keeping you isolated, serene, and profoundly relaxed. You are a silent observer of the cosmic clockwork, floating gently on the edge of the solar system, watching the slow, rhythmic dance of light and shadow. As you continue to float in the profound, undisturbed silence at the very edge of our solar system, picture this lonely ambassador of humanity, holding its steady gaze. The technology operating inside Voyager 1 during that moment in 1990 was not modern, sleek, or instantaneous. It was an intricate marvel of 1970s engineering, functioning perfectly in the deep freeze of space. Voyager 1 was launched on September 5, 1977. Its journey outward was not a straight, simple line, but a complex, a sweeping arc dictated by a rare celestial mechanic. The mission took advantage of a unique planetary alignment that occurs only once every 176 years. This specific arrangement of the outer planets, Jupiter, Saturn, Uranus, and Neptune, was first mathematically mapped out by aerospace engineer Gary Flandreau in 1965. Flandreau discovered that by using the gravitational pull of each giant planet, a spacecraft could be swung toward the next, a technique called a gravity assist. This grand tour trajectory allowed Voyager to reach the outer solar system in a fraction of the time it would otherwise take, riding the invisible currents of planetary gravity like a leaf on a slow cosmic river. To maintain its precise orientation in the dark, Voyager relies on tiny bursts of gas. Deep within the propulsion system, a series of small thrusters release puffs of hydrazine. These thrusters fire in microscopic bursts lasting just 10 milliseconds. That is 1/100th of a second. A breath so slight it is imperceptible, yet it is enough to gently nudge the 1.5-ton spacecraft, keeping its main antenna aimed squarely at the inner solar system, ensuring the camera remains steady. Notice how different the inner workings of this machine are compared to the digital devices we hold today. The camera that captured the pale blue dot did not use a modern silicon microchip. Instead, it relied on an older, analog technology known as a Vidicon tube. Developed originally in the 1950s for television broadcasting, a Vidicon tube works by sweeping an electron beam across a photoconductive surface. When the shutter clicked open, the light from our tiny, distant Earth struck this surface, leaving a faint electrical charge. Think of this process as a slow, deliberate painting made of static electricity. It took the electron beam exactly 48 seconds to read out a single frame of image data. As this beam swept back and forth, slowly converting light into voltage, the data was not beamed immediately back to Earth. It had to be stored. Voyager recorded this precious imagery onto an 8-track digital magnetic tape recorder. Imagine the quiet mechanical elegance of it. A physical ribbon of magnetic tape, half an inch wide, smoothly winding across metal heads in the absolute vacuum of space, carefully archiving the light of our home. This mechanical memory bank is like an ancient metallic loom, methodically weaving electrical pulses into a tapestry of zeros and ones, safely holding the data until the slow rotation of the Earth brought the massive listening dishes of the deep space network into the correct position to receive it. The creation of this specific image was the culmination of a long, historic quest for humanity to see itself from the outside. Throughout our history, we had never known what our world truly looked like from the black ocean of space. The very first time human eyes looked upon an actual photograph of Earth from beyond the atmosphere was on October 24, 1946. On that autumn day, scientists launched a modified V-2 rocket from the White Sands Missile Range in New Mexico. Strapped to this rocket was a 35mm motion picture camera, set to snap a frame every second and a half. The rocket reached an altitude of 65 miles, roughly 105 kilometers, just brushing the edge of space before falling back. The camera smashed into the desert floor at 500 feet per second, but the film inside was protected in a custom steel cassette. When the scientists developed that black and white film, they saw a grainy, curving horizon obscured by clouds. It was the first time we saw the curvature of our own home. From that grainy black and white curve, our perspective slowly widened as our engineering reached deeper into the void. On December 24, 1968, astronaut William Anders, orbiting the moon aboard Apollo 8, looked out the window and captured the famous Earthrise photograph. At that moment, humanity's camera was roughly 240,000 miles, or 386,000 kilometers, away from the planet. That image showed a vibrant, the half-lit blue marble rising above the stark, desolate, cratered gray surface of the moon. It was a profound shift in human consciousness, revealing a colorful, fragile sphere alone in the dark. A few years later, on December 7, 1972, the crew of Apollo 17 captured the first fully illuminated portrait of our planet, a photograph simply titled "The Blue Marble." They were approximately 18,000 miles, or 29,000 kilometers away, traveling outward toward the moon. With the sun behind them, the entire face of the Earth was bathed in light, revealing the swirling white weather systems over the deep blue of the oceans and the rust-colored sands of the African continent. Consider the immense leap in distance between those early lunar photographs and the image taken by Voyager, where the pale blue dot pushed our cosmic mirror outward to 3.7 billion miles. That is a staggering distance, more than 15,000 times further away than the astronauts who took the Earthrise photo. To bridge that gap, Voyager had traveled continuously for over 12.5 years, steadily moving away from the warmth of the sun. When the magnetic tapes finally spun down and the data was transmitted across those billions of miles, it arrived at the Jet Propulsion Laboratory in California. The process of reconstructing the image from raw telemetry was handled by a dedicated team of planetary scientists. It was planetary scientist Carolyn Porco who co-directed the design and execution of this monumental portrait sequence, carefully calculating the exposure times and camera angles required to spot the planets against the background stars. And when the data for the Earth frame finally trickled through the computers, it was scientist Candy Hansen who became the very first human being to lay eyes on the pale blue dot. She processed the black and white raw images, searching the digital static for the specific 0.12 pixels that represented our entire world. Finding it required matching the faint blip of light against the known background stars of the cosmos. What's happening now is a quiet realization of how far we have reached, both in physical distance and in our understanding of light itself. The reason Hansen and her colleagues knew to look for a bluish speck involves a centuries-old physical law. The mathematical explanation for why the Earth shines blue, the phenomenon of Rayleigh scattering, was first formally described in the year 1871 by the British physicist John William Strutt, who is better known by his title, the third Baron Rayleigh. Rayleigh discovered that sunlight interacting with molecules much smaller than its own wavelength will scatter. Because blue light has a very short wavelength, it scatters 10 times more efficiently than red light as it passes through the nitrogen and oxygen of our atmosphere. Over a century before Voyager was even a blueprint, a physicist studying the properties of light on Earth had defined the exact equations that would eventually give our planet its distinct sapphire signature in the deepest reaches of the solar system. At this very moment, as you rest comfortably, the physics of light, the mathematics of orbital mechanics, and the slow rhythmic sweep of Voyager's electron beam all coalesce into a single calming truth. Our world is a small, quiet participant in an incredibly vast and predictable universe. The planetary alignment that made the journey possible, the hydrazine thrusters gently firing in the cold, and the spinning magnetic tapes all tell a story of careful observation. They speak to the patience of human curiosity, extending our senses into the freezing, silent dark. As you breathe in, imagine the cool, clean emptiness of space surrounding the probe. As you breathe out, visualize the slow, unwinding ribbon of magnetic tape, capturing the faint blue light of Earth. Everything is functioning exactly as designed, moving at the perfect speed, suspended in the gentle, eternal clockwork of the cosmos. Picture the sheer physical scale of what you are observing. The pale blue dot is famous for rendering our entire world as a mere fraction of a pixel in a digital readout. But to truly grasp the delicacy of this image, we must look at the physical camera sensor inside the probe. The actual physical projection of Earth's light that landed on Voyager's Vidicon tube sensor measured exactly 0.001 inches across, which is roughly 0.025 millimeters. Observe how unimaginably small that is by bringing the concept close to home. A single average human hair resting on your pillow is approximately 3 to 4 times thicker than the physical footprint of our entire planet on that metal plate. To understand this feat of optical geometry, planetary scientists calculated a familiar equivalent. Capturing the light of Earth from 3.7 billion miles away is mathematically identical to standing in a wide open field and trying to spot a single silver dime located exactly 2 miles or 3.2 kilometers away from your eye. Our planet is substantial, boasting a diameter of 7,917 miles, or 12,742 kilometers, from pole to pole. Yet, across the great quiet ocean of the solar system, that massive sphere of rock and water is reduced to a microscopic speck, smaller than a grain of sand resting on the head of a pin. Examine the iconic photograph in your mind's eye. If you look closely at the dark, empty space surrounding the pale blue speck, you will notice a distinct lack of background stars. You might assume the deep space environment would be blazing with stellar light, but the background of the image is a solid, comforting black. In this darkness is the result of a very specific mechanical choice: the shutter speed. To capture Earth without completely destroying the image with the glaring light of our nearby sun, the camera's shutter was commanded to open and close in exactly 0.005 seconds, 5/1000ths of a second. This is akin to the rapid mechanical blink of a sports photographer's camera, trying to freeze a sprinter in mid-stride. In that microscopic fraction of a second, only the most intensely bright objects could register on the sensor. The ancient, distant stars simply did not have enough time to imprint their faint starlight onto the magnetic tape. Even from this incredible vantage point, plunging toward the edge of interstellar space, the sun remains a dominating presence. From Voyager's perspective in 1990, our sun appeared only 1/40th the diameter it appears from the surface of Earth. Imagine holding a tiny glass bead or the tip of a ballpoint pen at arm's length against the night sky. That is how small the sun looked. Despite this shrunken visual size, the sun was still shining brilliantly, registering as 16 million times brighter than Sirius, which is the absolute brightest star in our earthly night sky. The sheer power of our local star, reaching across billions of miles, is a quiet reminder of the immense energy anchored at the center of our solar system. Deep within the freezing, -355°F environment, how does a spacecraft maintain the warmth and electricity required to snap a shutter in 5/1000ths of a second? Out here, where the sun is just a bright bead in the dark, traditional solar panels are entirely useless. They would generate no power. Instead, Voyager 1 draws its lifeblood from an ingenious piece of technology: 3 radioisotope thermoelectric generators, commonly known as RTGs. Think of these generators as a high-tech, enduring campfire safely contained inside a metal cylinder. Inside the RTGs are small protective spheres containing plutonium-238, an unstable radioactive isotope. As this plutonium naturally decays, it emits a steady, highly predictable amount of heat. The ceramic pellets of plutonium glow with a dull cherry red warmth, completely isolated from the crushing cold of the surrounding vacuum. The predictability of this radioactive decay is like a slow, comforting heartbeat. Plutonium-238 has a half-life of exactly 87.7 years. This means that every 8.5 decades, the material will produce exactly half the heat it originally did. It is a slow, steady, and perfectly mathematically calculable winding down. To convert this glowing heat into electricity, the generators rely on a principle called the Seebeck effect, a phenomenon first discovered in 1821 by the physicist Thomas Johann Seebeck. By placing 2 different types of metal in a circuit, with one end heated by the glowing plutonium and the other end exposed to the freezing cold of space, a continuous electrical voltage is naturally created. There are no moving parts. There are no pistons, no spinning turbines, and no engines. There is only the silent, beautiful physics of temperature difference, creating a gentle flow of electrons. When Voyager 1 launched into the sky, these 3 generators produced a combined 470 watts of electrical power. By the time it turned backward to capture the pale blue dot 13 years later, that slow radioactive decay had reduced the available power to roughly 370 watts. Compare this to the electrical items in your own home. A standard kitchen blender or a few traditional incandescent light bulbs use more electricity than that. Yet, with a mere 370 watts, this lonely robotic outpost managed to keep its computer brains warm, run its gyroscopes, point its heavy lenses, and whisper its discoveries back across billions of miles. The efficiency of this design allows for a profound sense of peace, an entire scientific laboratory kept alive by the heat of a few glowing embers in the dark. What is happening now, as the probe coasts outward, is an interaction with an invisible environment. It is easy to think of deep space as a perfect empty void, but it is actually filled with the breath of our star. The sun continuously exhales a stream of charged particles, mostly electrons and protons, known as the solar wind. This plasma travels outward in all directions at an astonishing speed of roughly 1 million miles per hour, or 1.6 million kilometers per hour. Compare this to the most destructive forces on our planet. A Category 5 hurricane on Earth boasts wind speeds of around 150 miles per hour, capable of tearing down buildings and churning oceans. The solar wind moves nearly 7,000 times faster than that earthly storm. Yet out in the near vacuum of space, this million-mile-per-hour gale is completely silent, frictionless, and invisible. The pressure of this solar wind creates an enormous protective bubble around our entire solar system, called the heliosphere. As Voyager 1 floated through this region, it was continuously bathed in this quiet supersonic breeze, riding the outermost ripples of the sun's influence. Return your focus to that tiny speck of blue light suspended in the camera's scattered sunbeam. In the photograph, the Earth looks perfectly still, a frozen, tranquil dot hanging motionless in the dark. But the reality of its mechanics is a story of incredible constant motion. At the exact moment the camera shutter snapped, our planet was hurtling along its orbital path around the sun at a staggering speed of 67,000 miles per hour, or 107,000 kilometers per hour. Think about the sensation of riding in a car on a smooth, empty highway at 60 miles per hour. The Earth is traveling over 1,000 times faster than that daily commute, endlessly carving its elliptical path through the vacuum. Simultaneously, the planet is spinning on its axis, rotating at just over 1,000 miles per hour at the equator. Mountains, oceans, clouds, and billions of lives are in a state of constant dizzying rotation and forward trajectory. Yet, distance is a powerful filter. The immense expanse of 3.7 billion miles acts as a cosmic lens of tranquility, stripping away all the frantic speed, the loud storms, and the endless motion. Through the lens of the Voyager probe, a planet racing at 67,000 miles per hour is smoothed into an absolute, unwavering calm. Allow the quiet precision of these physical laws to soothe you. The perfect 87.7-year decay of the plutonium, the absolute certainty of the camera's 5,000th of a second shutter, and the mathematical geometry of a dime viewed from 2 miles away. All of these elements work together in perfect harmony. There is no chaos here, only the beautiful, predictable clockwork of physics. You are safe to observe this vast machinery, resting in the warmth of your own quiet space, while the silent, frictionless gale of the solar wind washes endlessly over the outermost edges of our celestial home. Allow your thoughts to shift from the freezing metal of the spacecraft to the composition of that distant, glowing speck itself. When we look at the pale blue dot, we are not merely observing a solid ball of rock. We are witnessing a delicate chemical signature suspended in the dark. The color we see is intrinsically tied to the exact mixture of gases wrapping our planet. The Earth's atmosphere is precisely balanced. composed of 78% nitrogen and 21% oxygen, with trace amounts of argon, carbon dioxide, and water vapor. This specific blend is incredibly rare in our solar system. For instance, Venus, our nearest planetary neighbor, boasts an atmosphere that is 96% carbon dioxide, completely obscuring its surface in a thick, yellowish-white haze. Mars has a razor-thin atmosphere, also dominated by carbon dioxide, which gives its sky a dusty, pale red hue. Only Earth shines with that profound, scattering blue light, a direct result of an oxygen-rich atmosphere. And the reason we have that specific 21% concentration of oxygen is due to biological life. Microscopic cyanobacteria in our oceans, along with the vast breathing forests of our continents, constantly exhale this gas through the process of photosynthesis. Therefore, the pale blue light captured in that pixel is not just a trick of the atmosphere. It is the visual evidence of life itself, breathing on a planetary scale. Reflect on what this means for you right now, as you lie breathing quietly in your room. Every time you inhale, drawing oxygen into your lungs, you are participating in the very chemical process that makes our world visible from 3.7 billion miles away. The biological rhythm of your chest rising and falling is directly connected to the slow planetary exhalation that turns our world into a sapphire beacon in the void. You and the Earth are functioning as one continuous living system, your quiet breath contributing to the global atmospheric composition. Notice the geometry of the solar system around this dot. In the wide-angle mosaic that accompanied the famous narrow-angle shot, scientists captured the plane of the ecliptic. This is the flat, invisible disk where the planets travel, much like grooves on a record. Because of gravity, the planets do not bob up and down wildly. They follow strict, orderly paths around the sun's equator. The mathematical predictability of this plane was established by Johannes Kepler in the early 17th century. Kepler formulated 3 laws of planetary motion, the first of which states that every planet moves in an ellipse, with the sun at one of the 2 focal points. This means our Earth, the pale blue speck, forever traces a smooth, predictable oval through space. This elliptical path causes our distance from the sun to fluctuate gently over the course of a year. At perihelion, our closest approach in early January, we are roughly 91.4 million miles away from the solar furnace. At aphelion, our furthest point in early July, we drift out to 94.5 million miles. Yet, from Voyager's distant, unblinking perspective, this 3 million mile variation is entirely invisible. The frantic changing of our seasons, the freezing winters and scorching summers, are all compressed into a single, unchanging point of light. The chaotic variations of our weather are smoothed out by the sheer scale of the cosmos. At this very moment, consider the concept of time delay, a fundamental limitation of physics that dictates how we perceive the universe. Because light travels at a finite speed, 186,282 miles per second, or 299,792 kilometers per second. The image captured by Voyager 1 was already ancient history the moment the shutter closed. When the light of the pale blue dot reached the camera lens, the Earth it showed was exactly 5 hours and 36 minutes in the past. Everything on that blue speck had already moved forward. The planet had rotated, people had gone to sleep, and others had woken up. Weather systems had shifted across oceans. The camera was not capturing the present moment. It was capturing a ghost, an echo of light that had long since detached from its source. This delay creates a beautiful, isolating buffer. Think of a stone dropped into a calm pond. The ripples take time to reach the shore. The light of Earth is a ripple spreading outward through the vacuum. By the time that ripple reached the probe, whatever anxieties or urgencies existed on the planet were already hours in the past, rendered completely harmless by the slow, unyielding speed limit of the universe. Deep within the radio systems that transmitted this image, engineers utilized a complex mathematical language to protect the data from the degrading effects of deep space. When Voyager sent the image back, it did not send a simple picture. It sent a string of binary code, ones and zeros. To ensure this code wasn't scrambled by the background radiation of the cosmos, the data was protected by Reed-Solomon error correction. This is a brilliant algorithmic technique developed in 1960 by mathematicians Irving Reed and Gustav Solomon. It works by adding extra, redundant pieces of data to the transmission. If a stray cosmic ray strikes the radio signal and corrupts a 0 into a 1, the Reed-Solomon algorithm acts as an automatic mathematical immune system. It detects the error and instantly repairs it upon arrival on Earth. This same mathematical immune system, originally used to protect the fragile image of our planet as it crossed the solar system, is now used in the laser reading mechanisms of everyday CD and DVD players in our living rooms. The mathematics that guard the silence of space are the same mathematics that allow a scratched disc to play a symphony without a skip. It is a quiet testament to the durability of human logic, stitching together the fabric of information, even when it is stretched across billions of miles. The physical hardware of the camera itself is a marvel of resilience. The optics of the narrow-angle camera were housed behind a quartz window to protect the delicate lens from the microscopic dust particles of interplanetary space. These tiny, floating grains of rock and ice, known as micrometeoroids, travel at tremendous velocities, sometimes exceeding 40,000 miles per hour. A strike from a single grain of sand at that speed could pit or shatter ordinary glass. The quartz window served as a silent shield, taking the invisible impacts of deep space while allowing the precious light of the planets to pass through unharmed. It is a metaphor for the profound safety you can feel right now, enclosed and protected, allowing the gentle light of the outside world to filter in without letting any of the noise or chaos disrupt your rest. Scientists discovered a profound sense of perspective in the aftermath of analyzing this photograph. The total amount of digital data that made up the image of Earth was shockingly small. In the 1990s, computer data was measured in kilobytes. The specific file that contained the pixel of our world was a mere 5.4 kilobytes in size. To put that into an everyday context, a simple text message sent from a modern smartphone containing a single emoji often takes up more digital space than the entire visual record of our planet, captured by Voyager. The entirety of human history, all our oceans, mountains, and civilizations, was mathematically encoded into a file so small it could fit on a tiny fraction of an ancient floppy disk. This immense compression of reality invites a deep, settling calm. When you feel overwhelmed by the complexity of daily life, remember the sheer scale of the 5.4 kilobyte world. All the loud noises, the pressing deadlines, and the towering buildings can be mathematically reduced to a whisper of data, a tiny, pale blue signal easily carried on a 20-watt radio wave through the freezing dark. The image also speaks to the profound longevity of celestial mechanics compared to human timelines. The Voyager probe, carrying the memory of that pale blue light, is not slowing down. In the frictionless vacuum of space, an object in motion stays in motion. Isaac Newton formalized this law of inertia in 1687. Because there is no air resistance to drag against the metal hull, Voyager 1 will continue to travel outward at roughly 38,000 miles per hour, indefinitely. It is calculated that in roughly 40,000 years, the silent dormant probe will drift within 1.6 light-years of a star named Gliese 445, located in the constellation Camelopardalis. For tens of thousands of years, long after our present concerns have faded into history, this tiny piece of human engineering will still be gliding through the dark, preserving the memory of a pale blue pixel, a silent monument to the moment a species stopped to look back at its own home. Allow that immense, stretching timeline to wash over you, smoothing out the edges of the present moment, leaving only the slow, eternal drift of physics. Delve into the immediate tactile reality of the spacecraft at the very moment it captured that famous image. It is easy to visualize deep space as merely a cold, empty blackness, but a closer examination reveals a rich, highly specific sensory environment. To understand how the pale blue dot was physically acquired, we must explore the unique materials and forces interacting on the outer hull of Voyager 1. Visualize the mechanical structure holding the camera steady. In an environment where the temperature plunges to 58 Kelvin, ordinary metals would warp, shrink, or become catastrophically brittle. To prevent the camera from shaking or shifting during its meticulous observations, the spacecraft's structural struts were manufactured from a specialized graphite epoxy composite. This material was chosen for a deeply comforting physical property. It possesses a near-zero coefficient of thermal expansion. This means that whether the probe is bathed in the harsh, unfiltered glare of the sun or submerged in the freezing shadow of a planetary eclipse, the struts simply do not change shape. They remain perfectly rigid, acting as an unyielding skeleton that refuses to shiver in the cosmic cold, ensuring the camera remains absolutely motionless. And turn your attention to the exact nature of the light arriving at the sensor. The specific color we perceive as the pale blue of our oceans and atmosphere exists precisely at a wavelength of approximately 470 nanometers. Light travels in waves, and the distance between the peaks of these waves dictates the color our eyes eventually decode. When the planetary scientists commanded Voyager to layer its images, the color filters used were highly specific optical gates. The green filter permitted only light waves measuring exactly 560 nanometers to pass through. The violet filter was even more restrictive, only allowing wavelengths of roughly 400 nanometers to touch the sensor. By capturing these precise slices of the electromagnetic spectrum, the camera was effectively harvesting individual, microscopic textures of light. It is intriguing to observe the physical cause of the golden sunbeam that so famously cradles our tiny planet in the final photograph. That glowing band is not a mistake, but a beautiful demonstration of optical diffraction. The narrow-angle camera was protected by a sunshade, a cylindrical aluminum baffle painted completely black on the inside. This baffle acted exactly like a hand raised to shield one's eyes from a brilliant spotlight. However, because the sun was located incredibly close to the edge of the camera's field of view, incoming sunlight grazed the physical rim of this aluminum shade. As the light scraped against the metal edge, the photons bent, spreading out into distinct rays. By pure mathematical chance, the Earth's orbit placed it perfectly inside the center of one of these diffracted, scattered rays, illuminating the dust mote in a streak of accidental geometric warmth. Examine the texture of the image itself. If you look closely at the high-resolution files of the pale blue dot, you will see a subtle, grainy static across the dark background. This visual texture is the direct result of background radiation. High-energy protons, known as cosmic rays, constantly streak through the interstellar medium. These particles originate from distant supernovae and ancient galactic events. As the shutter remained open, some of these microscopic high-speed protons physically collided with the camera's analog Vidicon tube, creating tiny, bright static points. The grain in the image is essentially the visual echo of exploding stars, captured alongside the peaceful reflection of our own world. To prevent the delicate, moving parts of the camera from completely freezing in this harsh environment, engineers employed an elegant thermal solution. Dispersed throughout the spacecraft are small protective devices known as radioisotope heater units, or RHUs. Unlike the main generators that provide electricity, these specific units are dedicated entirely to localized warmth. Each RHU contains a tiny pellet of radioactive material and produces exactly 1 watt of continuous thermal energy. Visualize these tiny glowing hearths tucked inside the dark metal casing, emitting the warmth of a single small candle. They quietly radiate heat against the metal joints and optical gears, keeping the internal environment just warm enough to function smoothly against the crushing chill of the void. Listen closely to the mechanical rhythm required to save this data. Inside the insulated heart of the probe, the 8-track digital tape recorder was springing into action. To record the telemetry, the internal motors pulled a ribbon of magnetic tape across the reading heads at a highly specific speed of precisely 0.53 inches per second. In the vacuum of space, there is no air to carry sound, but if you could press your ear against the metal casing, you would hear the steady rhythmic click and whir of these reels turning. It is a slow, methodical heartbeat, measuring out 0.53 inches of memory every second, securing the light of humanity onto a spool of iron oxide tape. You may find it soothing to know that while the vacuum of space is silent to our human ears, it is vibrating with electrical frequencies. Voyager 1 carries an instrument called the Plasma Wave Subsystem, designed to measure the density of electrons in the solar wind. As the probe drifted, this instrument recorded the microscopic oscillations of the plasma. When scientists convert these electromagnetic waves into an auditory format, the deep space environment produces a distinct frequency. The plasma wave oscillations hum at a frequency of roughly 3 kilohertz. If you could hear it, this translates to a pure, high-pitched whistling tone, resembling the gentle ringing sound of a wet finger circling the rim of a crystal glass. The space surrounding our pale blue dot is not an empty, silent tomb, but an ocean ringing with a high, quiet song. Imagine the scent of this distant environment. While a human could never breathe out there, the interstellar medium does possess a distinct chemical profile. Floating among the solar wind are complex molecules known as polycyclic aromatic hydrocarbons, or PAHs. These molecules are incredibly common throughout the universe, formed in the dying breath of carbon-rich stars. If you were to gather these molecules into an atmosphere you could breathe, the void would not smell like empty air. Instead, the chemical signature of PAHs strongly resembles the scent of hot metal, burnt matches, or the sharp, clean smell of ozone after a lightning storm. The frozen dark is subtly perfumed with the metallic residue of ancient starlight. Reflect on the artifacts bolted to the exterior of the craft, specifically the golden record. The tactile surface of this phonograph record is an encyclopedia of the physical universe. The cover is not merely gold-plated for aesthetics. A specific portion of its surface is electroplated with an ultra-pure sample of the isotope uranium-238. This was a deliberate scientific choice. Uranium-238 is highly stable, decaying incredibly slowly with a half-life of 4.468 billion years. This coating acts as an ultra-slow radioactive hourglass. If another intelligence ever intercepts the probe, they can measure the remaining uranium and calculate exactly how long the spacecraft has been drifting, down to the exact millennium. Etched into the lower right-hand corner of this golden cover is a beautifully simple diagram consisting of two circles. This engraving represents the hydrogen atom, the most abundant element in the entire universe. The diagram specifically illustrates the fundamental transition of a hydrogen electron flipping its spin direction. This specific, microscopic shift takes roughly 0.704 nanoseconds to occur, and it emits a radiation wave exactly 21 centimeters long. This etched symbol serves as a universal clock and ruler. By using the natural, unchangeable physics of a hydrogen atom, the designers provided a key to decode the playback speed of the entire record. These physical truths, the 0.704 nanosecond flip of an electron, the 4.468 billion year decay of uranium, the 3 kilohertz whistle of the plasma, and the 470 nanometer wavelength of blue light, all intertwine perfectly. They weave a fabric of absolute scientific certainty. There is immense comfort to be found in this precision. The universe is not a chaotic, unpredictable storm. It is governed by quiet, steadfast laws that operate just as perfectly on a microscopic atom as they do across a distance of 3.7 billion miles. As you trace the edge of the sunshade, the smooth face of the quartz lens, and the intricate gold grooves of the record in your mind, let the physical reality of this machine ground you. The warmth of the 1-watt heater units, pushing back against the cold, the steady rhythmic turning of the magnetic tape, and the unyielding graphite struts all hum with a sense of purpose and endurance. They are a testament to the safety of physics, a perfectly designed system resting effortlessly in the grand, sweeping mechanics of the dark. Tracking this sequence to its gentle, inevitable conclusion, we observe the meticulous process of shutting down humanity's furthest eyes. On February 14, 1990, at exactly 5:22, Greenwich Mean Time, the final shutter clicked closed. The progression of powering down the camera was not a sudden flick of a switch, but a methodical, step-by-step transition commanded from billions of miles away. First, the telecommunications subsystem aboard the probe received a specialized packet of radio instructions. Next, the spacecraft's central 16-bit computer parsed this code, translating it into a physical command sent to the imaging science subsystem. Step by step, the electrical currents flowing to the camera's analog components were intentionally severed. The tiny radioisotope heater units, which had diligently kept the lenses from freezing, were instructed to power down. Gradually, over the course of several hours, the temperature of the optical housing dropped from its functional baseline down to the ambient 58 Kelvin, or minus 355 degrees Fahrenheit. The 8-track digital tape recorder completed its final revolution, coming to a permanent, mechanical halt. The camera was entirely, beautifully asleep. While the spacecraft initiated its long rest, the process of assembling the pale blue dot on Earth was just beginning. Methodically, the Deep Space Network captured the returning data as a continuous stream of 8-bit binary code. In computer science, an 8-bit string can represent exactly 256 distinct variations. The software at the Jet Propulsion Laboratory read these strings one by one, mapping each segment to a precise numerical value between 0 and 255. A value of 0 dictated absolute pure black, while 255 represented maximum brightness. Pixel by pixel, row by row, the computers constructed the image, layering the numeric maps from the green, blue, and violet filters over one another. This painstaking, slow accumulation of data stitched together 39 individual narrow-angle and wide-angle camera frames, ultimately completing the famous 60-frame mosaic of our solar system. Following this historic transmission, Voyager 1 continued its step-by-step progression outward, sequentially piercing the invisible magnetic borders of our star. The journey unfolded gradually. In December 2004, the spacecraft crossed a boundary known as the termination shock. This is the precise mathematical threshold where the million-mile-per-hour solar wind abruptly decelerates, dropping below the speed of sound as it collides with the interstellar medium. The instruments aboard measured this sudden thickening and slowing of the plasma, confirming the crossing of a major celestial threshold. The next phase of this physical transition occurred on August 25, 2012. On this date, Voyager 1 achieved a monumental milestone by crossing the heliopause. The process was confirmed by two very specific measurable phenomena. The onboard particle detectors registered a massive, sudden drop in the low-energy particles generated by our Sun. Simultaneously, there was a sharp, dramatic spike in the detection of high-energy galactic cosmic rays, particles originating from ancient, distant star explosions. Through this exact step-by-step exchange of atomic particles, scientists verified that the probe had officially left the heliosphere, entering the pristine, unexplored ocean of interstellar space. Today, this silent messenger is currently located over 15 billion miles away from the pale blue speck it once photographed. That translates to an astonishing 24 billion kilometers. Because of this immense and continually growing distance, the process of communication has stretched to profound lengths. A single radio signal, traveling at the absolute maximum speed limit of the universe, the speed of light, now takes over 22.5 hours just to travel one way from an Earth-based antenna to the spacecraft. A simple greeting and a digital response requires a continuous 45-hour round trip through the silent dark. As you lie here in the quiet warmth of your room, permit your body to mirror this deep, cosmic winding down. Bring your awareness inward, away from the billions of miles of space, and trace the step-by-step process of your own physical connection to the universe. You are not separate from the celestial mechanics we have observed. You are a direct biological consequence of them. Within your very cells, a timeline of stellar evolution is written in microscopic detail. The hydration resting in your tissues, the water molecules sustaining your life, are built with hydrogen atoms. This specific element was created in the immediate expanding aftermath of the Big Bang, precisely 13.8 billion years ago. Every molecule of water within you has existed since the dawn of physical time, slowly cycling through nebulae, oceans, and clouds before resting inside you tonight. Trace the carbon that forms the structural foundation of your DNA. This element was manufactured through a specific sequence known as the triple alpha process. Deep inside the crushing gravity of ancient red giant stars, 3 helium nuclei were forcefully fused together over millions of years to create a single carbon atom. When those stars eventually exhaled their outer layers, this vital carbon drifted across the boundless quiet, eventually coalescing to form the pale blue speck, and subsequently, you. Consider the iron flowing smoothly through your bloodstream at this exact moment. Iron, which holds the atomic number 26, can only be naturally forged in the catastrophic core collapse of massive stars. In the final blinding fraction of a second before a supernova explodes, core temperatures exceed 3 billion degrees Celsius. That exact, terrifying threshold of heat is required to forge the iron that now binds to the oxygen in your hemoglobin. The rhythmic beating of your heart is pumping the direct remnants of detonated stars through your chest. Even the heavy, relaxing weight of your skeleton sinking into the mattress is a cosmic artifact. The calcium giving strength to your resting bones, an element bearing the atomic number 20, was synthesized in the intense pressure waves of those very same supernovae explosions. The step-by-step fusion of the universe has literally built the frame that supports you. You are, in the most literal, scientifically verifiable sense, a collection of ancient stardust, temporarily assembled to observe the cosmos from which you came. Just as your body prepares for the restorative quiet of sleep, the Voyager spacecraft is undergoing its own gradual, unavoidable descent into slumber. The radioactive plutonium inside its generators does not last forever. The physical decay of this material means the spacecraft's available electrical power drops by exactly 4 watts every single year. Engineers are currently managing a slow, methodical triage, turning off heaters and gyroscopes one by one to conserve energy. By the mid-2030s, the power will drop below the minimum threshold required to operate any instruments. The final sensor will close its eyes, and the probe will transition into a fully inert, silent piece of floating metal. Following this final shutdown, the journey will stretch into timescales that bring an overwhelming sense of peace. Without propulsion, navigating purely by the smooth, invisible rails of gravity, the inert probe will drift outward for roughly 300 years before reaching the inner edge of the Oort cloud. This is a massive, spherical shell of icy bodies surrounding our solar system. The spacecraft will then spend an unimaginable 30,000 years gliding silently through this frozen debris field. Once it clears the Oort cloud, Voyager will enter an endless, repetitive rhythm. It will become a tiny artificial moon of the Milky Way galaxy. Bound by the gravitational pull of the galactic center, it will complete a single massive orbit every 225 million years. Allow this unfathomable stretch of time to wash over your mind. The urgency of the present moment dissolves against a 225 million year orbit. There is no rush. There is no pressure. Everything unfolds at the exact pace dictated by the gentle, absolute laws of physics. Surrender to the heavy, comforting pull of your own local gravity. As you sink deeper into the mattress, envision the pale blue dot fading into a soft, indistinct glow. You are safe. You are anchored to a small, perfect world, sheltered by an atmosphere of scattered blue light, warmed by a distant star, and protected by the immense quiet buffer of deep space. I breathe in the quiet of the universe. I release the noise of the day. My body is resting, composed of ancient, peaceful stars. I am untethered from worry, floating in the gentle dark. My heartbeat slows to the steady rhythm of the cosmos. The gravity of the earth holds me completely secure. All things are moving perfectly, in their own time. I am a quiet observer, yielding to the silence. The space around me is clear, calm, and perfectly still. I embrace the heavy, comforting weight of rest. I am fading into the beautiful, unending dark. Good night.